Hey kiddos, and welcome to our last podcast. We're going to be taking a look at titration curves. Okay, so you know how to do a titration, you know how to do the stoic with the titration. Now we're going to take a look at the titration curves. Alrighty, so cool thing about titration curves is that it gives you so much information. We can get so much information from these titration curves. So let's take a look at definition. A titration curve is a graph of the pH vertical axis versus the amount of the reagent progressively added to the original sample. As the equivalence point is approached, there is a rapid change in the pH, and when a titration is done to create a pH curve, the addition of the titrant is not stopped at the end point, but is continued until a large excess has been added. And so let's take a look at what's happening, okay? So the initial addition of the titrant in the burette to the acid does not produce large changes. This relatively flat region of the pH curve is where a buffering action occurs. So this is what's going on here. If you take a look over here at this titration, you don't even have to look at the title. The title kind of tells you what's going on as well. But let's take a look at the very beginning of the curve. Notice at the very beginning of the curve, you have a very low pH. It has a pH of less than 1. So we know that this is your sample. This is what you're starting off with. You're starting off with your sample. Remember, the sample's in the Erlenmeyer flask, and to it you add your titrant, which is in your burette, right? So because we're just testing the sample, here, we can say that it's a strong acid. If you take a look at the very back side of the very end of the titration curve, right here, this is going to give us information about the titrant, what was added to the sample. And here, it's a pretty high pH, so we can kind of tell that it's a strong base. So that tells you from this pH, this titration curve, we know what the sample is, and we know what the titrant is, okay? So in the initial, let's just kind of annotate that. The initial addition of the titrant in the burette to the acid does not produce a lot of change, and this is called the buffering system. You don't really even need to know that. That's more of a Chem 30 thing, but it's just talking about this region right here where the pH pretty much stays the same, okay? As the titration proceeds and the base is added, right, in this case, some of the acid is reacted with the added base, but anywhere before the equivalence point, some excess acid will remain, so the pH stays relatively low. Very near the equivalence point, remember the equivalence point is when equal amounts of moles of the acid and the base react. Remember that? So very near the equivalence point, a small excess of acid becomes a small excess of base with the addition of a few more drops. So the pH drops abruptly. Okay, so that's right here. So this is kind of like the beginning of our endpoint. There's our end, like this is kind of our endpoint area. So that's that one extra drop of the sodium hydroxide that all of a sudden the color change, that's the endpoint, changes permanently, right? So at that point, we have a huge, just abrupt change in pH, and it really goes from no change to right away there's a change. Now, at this point, with our titration, this is where we stop. But for the titration curve, we add more and more NaOH to get us to this last part of the curve, right? So, very cool thing is this vertical area here. If I take the middle of that and I extrapolate it, we see that it's a pH of 7. So this is telling you that at the equivalence point, the pH is 7. The equivalence point is still the equal number of moles react, but the pH at the equivalence point is 7. The equivalence point is the center of this change where the curve is the most vertical. So you do that for every kind of curve. You take a look at the middle and you bring it over and you see what pH at the equivalence point is, okay? And then you can also say, hey guys, it took 20 milliliters of the base to reach the equivalence point or the end point. So let's take a look at the chemistry that's going on. You're taking your hydrochlorous, the two reactions are your sodium hydroxide. In this case, it was your titrant, right? And your hydrochloric acid was your sample in this case. And when it reacts, it forms water and sodium chloride or a salt. Let's take a look at our net ionic equation. Remember, we don't dissociate water. This is just the behind the scenes, what's going on behind the scenes to cause this titration curve. You take out your spectator ions and you get this net reaction, okay? That's what we're actually looking at. For convenience, hydrogen ions are written in their simplest Arrhenius form, but you can put hydronium ions, that's fine. Why was the equivalence 0.7? Why? Because look at your product, right? Water. Remember, water has a neutral pH of 7, and the spectator ions are neutral, so a strong monoprotic acid, strong monoprotic base titration must have a pH of 7 at the equivalence point. So equivalence point, it's important to note that the equivalence point, pH 7, is only for strong acid-base reactions, okay? Only for those. For every other acid-base reaction, the equivalence point solution will contain ions or molecules that are not spectators. So titration curves must be done empirically to determine the equivalence point. Okay, here's a general rule. Let's take a look at the general rule, and then I'll show you what that is. Strong acid to base, pH at the equivalence point is always lower than 7. When you have a strong acid and a weak base combo, the pH at the equivalence point is always lower than 7. When you have a strong base to weak acid combo, the pH at the equivalence point is always higher than 7. Well, let's see if that's true. So here's a strong acid added to a strong base. Take a look over here. That's our sample is a strong base. And our titrant is your strong acid. Center, 7. Okay, that's true. Strong base added to a weak acid. Okay, so here's our sample. It's much higher than 1. It's closer to a 3. So that's your weak acid. And take a look at this. This pH is about almost 14. So that's your strong base. Here's our vertical area. And there's the center of it, and the pH at the equivalence point is higher than 7. So here's a strong base added to a strong acid. There's our sample. It's a very strong acid. This is our titrant, a very strong base. Smack dab in the middle of this, pH is 7. Okay, this middle is more like here. pH is 7. Here's one, strong acid added to a weak base. So our sample is a weak base, and our titrant is a strong acid. There's our vertical region. If we take the middle of that, is that around there somewhere? And the pH is lower than 7. Okay, so that's how you annotate these pH curves. Strong acid, weak base, diprotic base. So why is it diprotic? Can I just show you really quick? If I take that and I dissociate it, I have 2 sodium ions, and I have CO3 2 minus. Okay, there's my base, and take a look at this charge. We see that it's a -2 charge, so it's going to react 2 times. Why does the curve start at the top? Why does the curve start at the top? Because now a strong acid is being added to a weak base, not vice versa. Okay, anyhow, let's just take a look at this. This happens because the base is diprotic, meaning that it will react with 2 hydrogen ions, so the hydrogen ions attach to the carbonate ions one at a time. Here's our first reaction, kiddos. Here's our second reaction. Anytime you have this kind of thing, you have 2 bumps. Okay, typically a titration curve looks something like this, or a titration curve will look something like that, right? But there's only one bump. There's only one vertical area. In this case here, there's a little wee bit of a vertical area, and here's your other vertical area. This is your first reaction. And this indicates your second reaction, right? Strong acid with your diprotic base again. There's the diprotic base reacting once, reacting twice, and it's just telling you that this reacts 2 times. 1 and 2. And when you're picking a indicator, you always have to pick the indicator for the second reaction, okay, kiddos? You will want to choose an indicator that changes color at the second equivalence point, but I'll show you how to pick indicators in just a bit. Strong acid, weak diprotic base. Why is the equivalence point less than 7 when you have a strong acid plus a weak diprotic base? Because when you look at your net ionic equation, right, what you have as one of your products is an acid, right? So at the equivalence point, there's neutral water. There's my there is neutral water, neutral spectator ions, and some weak acid. There's our acid. What do you think keeps the pH below 7. It's that acid, right? Why do we care about titration curves? Acid-base reaction pH curves provide a wealth of information, tells you the initial pH levels, and that's for your sample, right? That's talking about your sample. Equivalence point volume of the titrant, for sure, and the number of reaction steps. And the final pH, pH level talks about the titrant. That's really important as well. Oh, maybe I should erase that, and then we can read this. Equivalence point pH for the indicator selection. So the endpoint observed for the indicator chosen will closely match the equivalence point of the reaction. So let's talk a little bit about how to pick these indicators. Basically, when you're taking a look at this vertical space, anything that changes color in that vertical space is going to be an appropriate indicator, right? So thymol blue, for example, is an unsuitable indicator for this titration because it changes color before the equivalence point. So this color change happens way too low, with way too low of pH. And alizarin yellow is also unsuitable because it changes colors a little bit too high. The pH of the changing colors is too high. Bromothymol blue is suitable because its endpoint pH of 6.8, assuming the middle of the pH range, closely matches the reaction equivalence point of 7, and the color changes completely on the vertical portion of the pH curve. So as long as your indicator fits into here, the closer to here, the better, right? So you want to get it as close as you can to the pH at the equivalence point. But anything within this range is okay. Anything out of this range is not okay. Final tips. It is also critical that the amount of indicator used be extremely small. So you only want to add 2-3 drops maximum, 3 drops maximum to your sample, because you're always adding your indicator to your sample. Some of the titrant volume is used to react with the indicator to make it change color. But if the amount of indicator is very small, like 2 drops or 3 max, the volume of the titrant used this way will be very small, and the accuracy of the titration will not be affected. So let's summarize. An indicator for an acid-base titration analysis must be chosen to have an endpoint, or a permanent change of color, at very nearly the same pH as the pH at the equivalence point of the reaction solution. Make sure you're as close to that center as possible, but anything within that range will work. The pH of the solution at the equivalence point for a strong monoprotic acid, strong monoprotic base reaction will be 7. And the pH of the solution at the equivalence point for any other acid-base reaction must be determined experimentally by plotting a pH titration curve. Okay, so that's it for our last PowerPoint. Have a great day, kiddos.